Good morning, everybody. It's good to see you guys again after technical proposal. I'm glad we went through the second phase of the project. This is DC Square Engineering. I am Diana. I'm the project manager for the Bridge 9. I brought along my team of engineers, star engineers, which I'm going to introduce to you right now. This is Miguel Arbuela. He has done the environmental impact studies, as well as the aesthetics and the lighting. Danny Sanchez and Liana Lantigua, who are structural engineers. Emmanuel Perez, he has done our transportation geometric design. Kevin Zambrana, our geotechnical, as well as column and foundation design, along with Cecilia Posada, who works side by side to do the drainage in this project. And we have Chris Soto. He has done all the MOT construction schedule, and basically everything else. We're here to discuss Bridge 9, so is everybody else. Bridge 9 is part of the master plan for the 826, 836 interchange to alleviate the heavy traffic along these expressways in Miami-Dade County. The bridge goes from the northbound 826 to the westbound 836. However, in terms of construction, we'll be starting here, going south towards 826. As part of the project, this is 2,310 feet long, and as Manny has said,
just to give you a quick overview, this is going to be two 12 lanes and two shoulders, 8 and 11 feet respectively, and also it's going to have the two reinforced concrete traffic railing. Now I pass it on to Kevin.
Prior to our design phase, we conducted a subsurface investigation with the findings listed below. Found that the top layers consisted of sands and limestone fill, and we found the water table to be at +3 feet NGVD, and lime rock base to be between 40 feet and 75 feet below NGVD. With these findings, we give the following recommendations for our foundations: the use of 24-inch square pre-stressed concrete piles at a depth of 65 feet with a capacity of 25 tons in compression and 25 tons in tension.
Hello, my name is Miguel Arbuela. I'm going to talk about the environmental part. We are having into consideration the water quality, air quality, infrastructure, and wildlife. As for water quality, we meet all the requirements, especially for protecting all the wildlife and water that goes to the Miami C4 and structures. We take into consideration the terrain that goes under the bridge and also the airport structures as well. And for the air quality and noise, we are taking all the precautions based for all the possible agencies and requirements that are for our project. With this, we're going to start with the design of the project.
Okay, the geometric design was based on the FDOT PPM manual as reference, and as you can see here, using the design speed of 45 miles per hour, the maximum grade of the vertical curve is 5%. In our design, it's going to be 4.66%. It's very close because this bridge is going to be going over everything else that is already there. For the horizontal alignment, again using the PPM manual, the length of the curve should be over 1,350 feet. In our design, it's going to be 1,884 feet, and the radius is going to be 1,372 feet. For the super elevation, the minimum required is 0.061. In our design, as you can see here in the super elevation diagram, it's going to be 0.064. Now, jumping to another subject, there are two different casting methods available. The first one is the long line casting, which is where all the segments for a span is done simultaneously along the bed, so it looks like the real structure. For this one, you require a large area to cast it. So for our case, it's not good. So we're going to use the short line casting, which is done in each span individually, and always using the previously cast segment to perfect fitting and also for the geometric purpose. Now I pass it on to Kevin.
Thank you. Using the FDOT precast yard, we establish once we're doing the forms, we're going to do them before releasing and moving. The concrete has to be at least at 3,000 psi. After that, it's going to be set to be cured, so it reach at least 6,500 psi and 28 days, so it can be used to be placed on the segment. For the gantry construction, we established a budget for the rental cost of $4 million. The assembly time will be approximately 6 weeks, and the disassembly time will be about 4 weeks. Space-wise, we established that the gantry weight is going to be about 950 kips, and will have a total length of 460 feet. Also, once we're doing the aeration process, the gantry will have an amazing speed of 0.8 feet per second. Now I'm going to go into Liana, which is going to pretty much explain the design loads of the project.
Hi, my name is Liana. After analyzing service and construction loads, we have concluded that the construction loads are be critical for the design of the structure, since we're using a gantry. The specific gantry that we're using for this project is not long enough to hold its legs on both piers at a time. Hence, at some point we're going to have the rear leg of the gantry on the fixed segment. This means that that's going to be the critical moment when we have to determine the loadings on the structure. The critical span is going to be 6 and 7, adjacent to pier number 7, so it's going to be the longest and the most number of segments. And each segment is going to have approximately 9 kips per foot. That's going to be the dead load on the structure. The maximum moment is going to be 25,000 kips foot, and it's going to happen again when we have the gantry leg on the fifth segment of this span.
For our bridge now, 9 foundations, we use the loads as said by Diana. Here we see the foundation for Pier 7, which has the longest span on both sides. Our layout will be a 34-foot by 34-foot, 7-foot deep outcap, 6,000 psi, with the layout of our 24-inch precessed concrete piles as shown, spaced at 6 feet apart. Our reinforcement will be, our top layer will be number 11s at 10 inches on center, and our bottom layer will be number 11s at 6 inches on center. Okay, here we see a rendering of Bridge 9. The red arrows indicate our columns, which are in critical locations, which we have to place them. If not, our spans will go from 200 feet average to 400 feet. Here's a close-up going northbound, and another one going eastbound. So for our columns, we took an innovative approach for our columns to use structural styrofoam in our hollow core. So as you can see in this sketch, our first pour will be our base pour, solid pour, and our cap will be solid as well. In between those two pours, we'll use the polystyrene structural styrofoam in between. And on the left-hand side, we can see typical reinforcement for our column.
So here we have what the typical section for the segments look like. These are the dimensions that we have, and as Manny said previously, we have railing barriers that are reinforced concrete, and the interior one is going to be 32-inch tall, while the exterior one is going to be 42. It's going to be a precast segmental structure with a concrete of 7.5 KSI and the F shapes for the railing barriers. This is what the reinforcement and the post-tensioning segment will look like. On the top we have cantilever post-tensioning, and on the bottom we're going to have the final post-tensioning providing for continuity, as Diana is going to explain right now.
Okay, just to add a little bit more with Liana and Diana in construction, we are going to have segmental box girders, as FDOT was trying to encourage for this project. For the construction of segmental bridge girders, you have on the top of your box cantilever tendons. These will allow to join each pier as you construct. We'll add on the pier and then add on segments on each side and then post-tension them, jacking them until you reach the end of your spans. Not the end, I'm sorry, the critical section of your spans as you design. Each span has different lengths, therefore different number of segments. The segments on the side of the pier are thicker. This being less thick at the middle will provide less moment, will make less moment as having the sections being smaller. Once the segment is completed, a cast in place will join the two segments to complete a span, and a hard post-tensioning tendon will be done to create continuity as well as any flexure, any bending moment, resist any bending moment of the span.
So, for the erection process, as you can see on the diagram that we have on the screen, we established an erection process starting from the west side of the bridge to the south side. We're going to start pier number 2. At the beginning of the span, since they're too short, we won't be able to put the supporting legs at the piers. Afterwards, you can see on the bottom picture, once we start reaching to longer spans, we're going to start placing our rear supporting legs at around 50 feet away from the last pier section erected. Here you can see a summary pretty much of what the erection will look like. As you can see, the main goals will be, once we set the pier at the segment, we're going to stress it with a vertical PT bars at 150 kips. Later we're going to start, as we erect each segment, we're going to be adding temporary bars, followed by installing and stressing cantilever tendons. From there, once we finish or complete the erected section, we're going to do our form and pour for the closure part of the midsection. Afterwards, we'll remove the temporary PT bars and then install and stress our continuous tendons part. And now Cecilia will explain the drainage process of the bridge.
Okay, drainage. Based on our research calculations using the rational method and also the FDOT-IDF equations for our region, which is region 10, also basic hydraulic criteria and specifications provided by us from the responsible agencies, the design to meet the federal, state, and local stormwater criteria according to the improvements for the drainage for the Bridge 9, which is located within the boundaries of the South Florida Water Management District. As you can see, the designs include 10 drain inlets that are located on the left side, and you can see the 8 inches ductile cast iron pipes that are used from the midspans to the columns. The drainage system goes through the columns acted by the gravity. We use type 2 catch basins, 6 inches PVC pipes, and also we use splash pads that are at the bottom for the water flow control. Placement of the bridge reinforcement was adjusted as necessary to provide a minimum of 2 inches of concrete cover, and the top of inlets was recessed to 1/2 inches according to the requirements. We use the PVC pipes in order to avoid the corrosions inside the structures, and all of PVC pipes conform to the requirements from the American Society for Testing and Materials. In addition, it is very important that offsite discharge do not affect already existing offsite properties. So the runoff is routed using drainage basins, and each of the drainage basins consists of roadside wells with French drain system installed underground. 3 ponds are part of the system with 48 inches French drainage, and the runoff may impact portions of the north-lying canals. All of the systems within the project is self-contained, and since we use French drain systems, we were able to retain 100% of the contributing runoff with no offsite discharge, which means that our water quality criteria was successfully met.
For the aesthetics of the bridge, this is going to be the columns. The panels we're going to use are 4 feet and an inch times 4 feet and an inch. The palm front silhouette from the MDX and Hinchman model, we're going to use the column 3 suggested by them. For the bridge itself, we're going to use column 1 and 2 that is for the bottom part and for the top part as well. For the lighting of the structure, due to the proximity of the project to the airport, the height of the poles will change between 15 feet and 20 feet. This section here, the length is gonna vary. It's gonna stay equal. For this bridge, we're gonna use the S-stream due to the illumination and based on the backlight, forward light, and uplight of this light. And as you can see here, you can show what's the illumination of this. We're gonna use 50 lights located at 46.2 feet each due to the optimal illumination of the bridge. Now, with this, we finished the design. I'm going to introduce you to Chris. His kid.
How's it going? Chris Bristow, construction engineer. As you can see behind me, there's a baseline construction schedule for our construction process utilizing the P6 program. Over here, as you can see, on July 29th, we have our expected notice to proceed for the project, and our project expectancy will be from 14 to 16 months, which will end on November 24th, 2016. Over here, as you can see on the right, you have critical dates, amount of days for each part activity in the project. You have your substructure, your superstructure, and your drainage. Drainage being parallel construction with those two along our schedule. Over here on this side of the schedule, you'll see that you have your substantial completion date, which is November 8th, which is actually the date which we give the contractor goes through their punch list, and they go through the demobilization for the project end that we expect on November 24th, 2016. Over here, you can see that these are our critical sections for MOT. Our maintenance of traffic is, FDOT gave us the idea to not close any lanes during construction, so night work is going to be utilized for these critical moments in our construction path, because these are the moments that we go over existing traffic. Over here you can see this is a drawing, just a base drawing, utilizing FDOT standard specification 613, double lane closure. Over here, this type of drawing will then be certified by an advanced MOT personnel, which then will be submitted through FDOT LCIS program, which we need we're going to assure the 2 weeks that you have every approval takes 2 weeks to do along this process, and then traffic control officers will be utilized throughout all nightly closures. Over here, these are some examples of your FDOT LCIS attachments for your closures. Over here you have the eastbound 836, westbound 836. And now over to Diana for estimated costs.
For estimated costs, we took into account past experience for our company, past experience in box girder construction, as well as the FDOT manual on the FDOT website for current and updated cost. Our total cost right here is $17.6 million for the bridge construction. Please know that $4 million of that is only the rental of the gantry. However, by sharing it with the other 3 bridges that are being segmental box girders, that will allow for a quicker start of construction, as well as perhaps a cost cut in the estimate. $9.1 million on our superstructure, 6.6 on the substructure. We have about 2% in general conditions, which allows for equipment move and demove, anything, payment and performance bonds, temporary site offices, temporary toilets, etc. Also, in the 17.6, you want to know that it's about $150 per square foot. This has been based in an efficient and also a safe and cost-effective design by us. This will conclude the presentation, and we'll open to any questions.
I'm sorry, what was the length of your project in days?
14 to 16 months.
14 to 16 months?
Yeah, you could that be 14 to 16 months.
What's the schedule say? I mean, what is your baseline schedule?
Baseline schedule.
Actually, in terms of days.
We have
350.
yeah 300.
Okay, and you're working, what, 5 days a week?
Work will be utilized during the day for segment placement, but whenever we come into those existing conflicts, we're going to go with the nighttime work. That's the only time we ever close roadways.
What about weekends, though?
No work. This is 337 work days.
Work days.
Okay.
Gotcha. Real quick, since you're on the schedule, it shows your critical path going through your superstructure segment.
Yes.
Superstructure segment. And then installing the superstructure segment, however you got your, looks like you got your foundation poured after building your superstructure.
Foundation. Yeah, right here.
Shouldn't you come up with your foundation first and then start
We were trying to work it out parallel. Therefore, when you have foundations and columns on one side, we can begin our superstructure.
So that's for different sections?
Yes,
Yeah.
still in sections.
Comment, I like the team color coordination. First thing I noticed. At the beginning, the presentation seemed a little rushed, and it was hard to kind of like catch up and get any notes. I'll ask the same question I asked for the second group. What is the critical loading of the bridge?
It's for the moment on the face of the pier number 7, which is the longer span, and it's going to happen when we have the rear leg for the gantry on the 5th segment of the span.
So the greatest load the bridge will ever experience
It's
is
under construction when the gantry is moving over the segments.
In terms of moment and shear. Is that what you're asking?
Yeah.
The loading?
yeah, the actual,
Yeah, what's your actual loading?
It's around
Design load.
24,000 cubic foot.
Okay. I think that's what you're asking.
Yeah. Or what's the max load the bridge is ever going to experience?
20 to 30.
During
Construction, we have due to the
Right.
gantry.
You got that, group 2? Roadway seems to be constrained by the columns in one of your drawings. I think it was mentioned. Are the columns in the clear zone? Would you say it's in the clear zone? And
Go back to the slide. Well, to answer, yes, they are in the clear zone, but we would need to add barriers around those columns to ensure that they don't get hit.
yeah, I was looking at the previous slide. I guess that's that one. Yeah.
Yeah, this is before the variable speed.
Okay. That's all I have. Good presentation.
I like the way the PM changes on the slide.